When you push a 1.6 trillion parameter neural network to ingest a single, continuous sequence of 1 million tokens, the physical hardware eventually breaks. The breaking point is the KV cache. Under standard grouped query attention, simply storing the attention history for a single 1 million token stream consumes over 4 gigabytes of memory. Now, scale that requirement to production levels. Serving hundreds of concurrent users no longer requires just high compute. It requires petabytes of VRAM dedicated solely to memory retention. DeepSeek-V4 processes that identical 1 million token context through a 1.6 trillion parameter architecture, but collapses the KV cache requirement to roughly 82 megabytes per stream. This split panel illustrates exactly what that means, a 98% reduction in memory footprint compared to the standard baseline. You cannot achieve extreme scale simply by provisioning larger GPU clusters. You have to optimize the architecture directly against hardware physics. Advancing foundational AI at this level requires strict mathematical bounding. It means fixing the residual stream, compressing sequences, and co-designing the algorithm with the hardware. Consider the residual highway. Standard networks use a narrow, one-dimensional vector. Expanding this stream into a two-dimensional matrix, a hyperconnection, allows the network to reuse multiple streams of features simultaneously. But an unconstrained hyperconnection matrix carries a severe numerical flaw. Its spectral norm, its largest singular value, often drifts strictly above 1.0. This graph models that drift over depth. When a multiplier even slightly larger than 1 is applied across a deep stack of 60 layers, the signal amplifies exponentially, causing the network gradients to explode. DeepSeek-V4 resolves this via manifold-constrained hyperconnections. The network mathematically forces the transition matrix into the Birkhoff polytope, a strict geometric space where every row and column sums exactly to 1. By executing 20 iterations of the Sinkhorn-Knopp algorithm, the matrix is bound to this doubly stochastic property. Doubly stochastic matrices share a crucial mathematical invariant. They are entirely closed under multiplication. Their spectral norm is bounded exactly at 1. This geometric constraint guarantees that signals passing through arbitrary network depths remain strictly non-expansive. The risk of catastrophic gradient explosion during pre-training is completely eliminated. That same mathematical discipline solves the 1 million token memory wall. DeepSeek abandons standard grouped query attention for a dual-path hybrid attention architecture to process vast contexts linearly. This flow diagram maps the first path, compressed sparse attention. Consecutive tokens are compressed into 4-token blocks using local positional softmax. An FP4 lightning indexer then scans the entire sequence, doing rapid low-rank projections to pull only the top relevant pieces into high-precision memory. Because extreme compression can destroy immediate syntax, the architecture runs a parallel, uncompressed sliding window of recent tokens, preserving fine-grained local dependencies right next to the query. The second path, heavily compressed attention, trades precision for scope. It bypasses sparse selection entirely, dense packing the macro structure of the whole sequence at a massive 32:1 compression ratio. Giving a model an aggregated view of a million tokens introduces hallucination risk. When a specific query has zero relevant context in the past sequence, a standard softmax function still forces the probability weights to sum to 1, assigning arbitrary attention to irrelevant background noise. This equation shows the architectural fix. DeepSeek adds a learnable attention sync logic directly to the denominator of the softmax function. By introducing this extra term, the network gives the query head a mathematical escape hatch. If no relevant information exists in the sequence, the total attention mass across the context tokens safely drops to near zero. You get a 98% memory collapse, because the model successfully interleaves sparse local indexing with massive global compression, while giving the network permission to explicitly ignore irrelevant history. Scaling to 1.6 trillion parameters also breaks traditional optimization. Standard algorithms like AtomW compute parameter updates coordinate by coordinate, treating massive 2-to-2 matrices as flat lists of scalars. At this scale, pointwise scalar updates unevenly stretch the parameters, severely distorting the actual geometry of the linear transformations. To correct this, DeepSeek-V4 applies the muon optimizer across all 2D matrices. Muon uses momentum orthogonalization, ensuring every parameter update aligns perfectly with the manifold of the matrix itself. The mathematical ideal for orthogonalization is singular value decomposition. But exact SVD requires complex eigenvalue math that stalls the highly parallel architecture of GPU tensor cores. This formula reveals how Muon bypasses the hardware bottleneck. It executes a 10-step hybrid Newton-Scholz polynomial iteration, reducing the complex orthogonal update into pure matrix multiplication. The first 8 steps rapidly contract the singular values of the momentum matrix. The final 2 polynomial steps then lock the singular value spectrum precisely at 1.0, generating an approximately unitary matrix using only standard multiplication. Mapping complex orthogonal rotations directly onto tensor core-friendly operations yields a massive 35 to 40% gain in token convergence efficiency during pre-training. Optimizing the math inside the layer does not solve the physical gap between server nodes. In a giant mixture of experts model, routing specific tokens to specialized experts requires massive cluster-wide network communication. On standard commodity network fabrics, this all-to-all data transfer forces the actual GPU compute units to sit idle, waiting for tokens to arrive before they can perform any arithmetic. DeepSeek-V4 mitigates this idle time through fine-grained expert parallelism. The active experts are partitioned into 3 highly pipelined execution waves. The pipeline overlaps the initial network dispatch of one wave and the final result combination of another, burying that latency perfectly underneath the heavy matrix multiplication compute of the middle wave. By scheduling communication and compute to run simultaneously across the pipeline, this overlapping geometry delivers a theoretical 1.92x speedup over sequential execution. Intelligent pipeline scheduling takes a severe hardware limitation, commodity network latency, and hides it entirely underneath necessary compute. This rigorous internal architecture translates directly into external performance. On screen are the resulting benchmarks: 93.5% on LiveCode Bench, a Grandmaster ELO rating of 3206 on Codeforces, and an 80.6% resolve rate on SWE Bench. The true operational capstone is its memory reliability, achieving flawless 100% retrieval success across the entirety of the 1 million token needle in a haystack benchmark. For machine learning engineers, the architecture yields 3 practical takeaways. First, context scaling is no longer permanently tethered to physical VRAM limits, provided you deploy hybrid FP4 compression and attention sinks. Second, pushing models to arbitrary depth requires manifold-constrained residual matrices to prevent divergence, far beyond what standard layer norms can provide. Third, extreme scale optimization must abandon scalar approximations. You have to use hardware-native orthogonization, like the Muon optimizer, to maintain parameter geometry. DeepSeek-V4 proves that true foundational capability requires mathematically disciplined architecture, moving the industry beyond the simple brute force allocation of raw compute.